Today we're going to be starting on Chapter 5. Chapter 5 is also on probability, but it is a different type of probability than what we did in Chapter 4. Chapter 4 involved mostly the classical probability with rolling die and flipping coins and drawing names out of a hat and drawing cards and things like that. And in this chapter, we're going to be talking exclusively about what are called discrete probability distributions. And discrete probability distributions, for the most part, are tables that list the probability of different events being able to occur, and we're going to be working with those tables. It's very different from Chapter 4. Chapter 4 is really the only chapter that we do the more traditional probability. So we're going to do this chapter on probability, and then when we get to Chapter 6, we're going to be back to statistics. And from Chapter 6 onward, we're going to be talking exclusively about normal distributions, which are the bell curve distributions. So let's get started with Chapter 5. So this, of course, is Section 5.1. And we're going to kind of get this introduction to what probability distributions are, and our learning objective is construct a probability distribution for a random variable. Even more than constructing the probability distributions, we're going to learn how to read them and the criteria for them. Not really going to be constructing them on our own that much. So with probability distributions, we need to remind ourselves what a random variable is. We've talked about this before, but a random variable is a variable whose values are determined by chance. So again, we're still talking about like rolling a die, flipping a coin, drawing a card, drawing a name out of a hat, those types of things that happen by chance. A discrete random variable is still a random variable, of course, but it can only obtain specific values. So when you roll a die, you can only get a 1, 2, 3, you can only get 1, 2, 3, 4, 5, or 6. You can't get numbers between 1 and 2 or between 2 and 3. So you can't say it's any number from 1 to 6. It's any whole number from 1 to 6. So discrete meaning, as we talked about in Chapter 1, discrete meaning like a counting number. Again, with the probability distributions, it doesn't necessarily have to be a counting number, but you still have to be able to specify that it can be these very specific values. A continuous random variable, on the other hand, can assume values in between two given values. So you're talking about things like weight or length of time, things like that, where you can partition off the measurements. So with weight, yes, you could round to the nearest pound, but you could also round to the nearest tenth or hundredth or however small of a measurement increment you needed. And then a probability distribution is a table, as I mentioned, or function. We don't really do functions in this section, but it could be a function, meaning like an equation. Mostly it's going to be a table that describes the chance that a random variable takes on a specific value or values. So let's look at what these look like. So in this chapter, it clarifies that we're going to be talking about discrete probability distributions. So the ones that can only obtain specific values, which consist of the values that a given discrete variable can take and the corresponding probabilities. So if we look at the different sides of a die, got a visual here of the die, and we have a probability distribution of rolling a single die. Across the top here, you have all the possible outcomes. So 1, 2, 3, 4, 5, or 6. On the die it's represented by 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, 6 dots. So those are the possible outcomes. Then with those, in the probability distribution, we simply list what's the probability that will occur. Well, because the die is a fair die, we're assuming, then that means each side is equally likely to occur. So each side has a 1 out of the 6 sides chance of happening. And so we list that probability underneath it. So the probability of getting a 1 is 1/6. Probability of getting a 2 is 1/6, and so on. Okay, so that's a probability distribution. That's what they look like. So if we're going to construct a probability distribution, let's look at one that's a little less simplistic than just rolling a die. When we construct a probability distribution for the sum of rolling 2 dice, so for instance, this right here would be 2 because we got a 1 and a 1, which totals to 2. We can look anywhere in the table. This would be 9 because you got a 5 and a 4, which totals to 9. So our options are we can roll anything from a 2 up to a 12. That's the biggest we can get because 6 and 6 are the largest two rolls that we can get. So the sum, you'll notice 1 is not listed because 1's not possible when you're rolling 2 dice. So we start with 2. Again, that's the smallest we can have up here in the left-hand corner. And then we go up to 12, which is the largest you can have down here in the right-hand corner. And then we're going to calculate the probability of each of those occurring. Now, it's not evenly distributed like it is with rolling a single die. We have a better chance of rolling some numbers than other numbers. So let's see if we can figure out what those probabilities are. So if we look in this probability or this sample space that they have drawn out here, when we look at the number of possibilities, there's 6 this way because this lists the red die going from 1 to 6. And then along the top, this is the white die 1 to 6. And when we total that up, it's 6 down, 6 across. So there's 36 ways to roll the die. So everything is going to be, or at least start with, being out of 36. So let's look at how many ways can we roll the 2. Well, we saw it this way, the 1 and the 1. And that's the only way you can roll a 2. You cannot get a 2 for a total, for a sum, without rolling a 1 on one of the die and a 1 on the other die. So the probability of rolling a 2 is only 1 out of those 36 rolls is a 2. So now let's look at our ways to roll a 3. Well, the ways to roll a 3 are either to get a 2 and a 1 or a 1 and a 2. Those are the only ways to roll 3. Everything past that is going to be bigger because everything past that, one of the die is a 3. One of the dice is a 3, which would mean that the total, the sum, would be more than 3. So we only have these 2 ways of summing to 3. So we have a 2 out of 36 chance of rolling a 3. And then we're going to continue. And these are conveniently located in diagonals. You may not have noticed that before, but hopefully you'll see it now. So if we want to get the totals that sum up to 4, they're going to be in this diagonal right here. Okay? We can get a 3 and a 1, a 2 and a 2, or a 1 and a 3. So there's 1, 2, 3 different ways to get a sum of 4. So a 3 out of the 36 different ways sum to 4. Okay, now let's go to 5. And again, it's going to be along a diagonal. So if we start with 4, 1, that would be our first one. And then we're going to go up here to 3 and 2, 2 and 3, and 1 and 4. Those are the ways to get a sum of 5. 4 on the first die, 1 on the second die, 3 on the first die, 2 on the second die, 2 on the first, 3 on the second, 1 on the first, 4 on the second. Those are the 4 ways to do that. So 4 out of 36. All right, now we're going to go up to 6. We're going to start with 5 and 1, and then 2 and 4, 3 and 3, 4 and 2, 5 and 1. Okay, so we have 1, 2, 3, 4, 5 ways. Hopefully you're noticing a pattern here. It went 1 out of 36, 2 out of 36, all the way up to 5 out of 36. Okay, so is it just going to keep getting bigger and bigger until we're up to 11 out of 36? Let's see. All right, to get a 7, we could have a 6 and a 1, a 2 and a 5, a 3 and a 4 and a 3, a 5 and a 2, or a 6 and a 1. So all along this long diagonal from corner to corner, starting with 6 and 1, going all the way up to just 1 and 6. But everything in between those on that diagonal, 5 and 2, 4 and 3, 3 and 4, 2 and 5, also total to 7. So let's see, what is that? 1, 2, 3, 4, 5, 6, unsurprisingly, because we were up to 5 out of 36. Now we're up to 6 out of 36. So let's look at 8. Well, when we go to 8, we're going to start with 6 and 2, and then we're going to go to 5 and 3, 4 and 4, 5 and 3, and 2 and 6. And that goes down because now we're past the longest diagonal. The longest diagonal was across this way. That was the longest diagonal. Now we're going to a shorter diagonal, so it actually goes back down to 5 out of 36. And then I'm just going to kind of finish up quickly, hopefully you're understanding. The next one for 9s is only 4 out of 36. 10s are 3 out of 36. And then when we get to 11, there's only 2 ways to make an 11, either 6 and 5 or 5 and 6. And then there's only one way, just like with the 2, there's only one way to make a 12, and that's a 6 and a 6. That's the only way to get a 12 is a 6 and a 6. So now we have our probability distribution table, and there really wouldn't be anything wrong with leaving it like this. You could argue that this is a good way to leave it because it clearly shows where those numbers came from. But sometimes you're required to reduce your fractions or to switch it to a decimal. So let's just do that, and we'll add some extra rows on here. But again, this is a probability distribution table. Okay, this is complete, and you could stop there and say I have a probability distribution table. But let's go ahead and reduce it. Now, 1 out of 36 can't be reduced because we already have a 1 on top. 2 out of 36 could be reduced to 1/18. 3 out of 36 could be reduced to 1/12. And you don't have to do these in your head. You can do them on your calculator. Remember, we talked about how you could just type those in and then hit equals. Let me actually pull that up. So hopefully you got really good at this in chapter 4, but you don't have to reduce 436 in your head or on your own. You're welcome to just, type in 436 on your calculator and hit enter, and it will reduce it for you. Okay, so 436 reduces to 1/9. 536 does not reduce because there's nothing that goes into 5 and also goes into 36. So 536 is already reduced. 636, 6 goes into 6 once, 6 goes into 36 6 times. We have another 536, and again, then we're just repeating. So 436 again reduces to 1/9, 336 to 1/12, 236 to 1/18, and 1 out of 36 is just 1 out of 36. And then we can change all of those to decimals. So when we're, what did it do to me? So we can put it in as a fraction and then use our F to D button. So since I already have 1/9 in there, I'll leave that there. So 1/9 is 0.111. This is kind of small to write in, but then we have 1 out of 36. I like to do these when we're trying to actually reduce them to or change them to a fraction or a decimal. If you just put it in as divided, it'll give it to you as a decimal. So 0.02, I think it was 8. Yes, 0.028. 1/18 is divided by 18 would be 0.555, so 0.56, 0.056. And then if we go to the 1/12th, we get 0.083. And then 5/36. We get 0.139. And then 1/6 is the last one we really have to type in the calculator because then we can copy from the other ones. So we do our 1/6, which is 0.167. And then we can just write down from the other side, 5/36 was 0.139. 1/9 was 0.111. 1/12 was 0.083. 1/18 was 0.056. And 1/36 was 0.028. So the reason that I did all three versions is because sometimes in the explanations in ALEKS and such, it will give it in the reduced fraction form or in the decimal form, and students will be confused as to where it came from. So what I would recommend that you do is when you're looking at the probabilities and you're like, where did 1/9 come from? Where, I don't see where that came from. What you may actually want to do when you're looking at the explanations is you may actually want to go in reverse. And so when you see that one of the fractions is in 36, try changing all of them to that biggest number. So, you see 1/36 and 1/18, well, change the 1/18 to 2/36. Now that you will have to do in your head, but you're going to multiply, in this case, 18 times 2 gets you 36, and 1 times 2 gets you 2. Okay? And if you do that, then it's easier to see, well, the 1 came from one way, the 2 came from two ways, but the 36 is because there were 36 things in the sample size. It's not always that the largest number is the size of the sample space, but it will help sometimes. So I just want you to understand that when you're looking at the answers in ALEKS or in the textbook, they're going to give it in reduced form, but the problem with that is sometimes you can't recognize where it came from as easily. All right, so now that we've constructed a probability table, let's look at another way that you can represent the probability distribution, which is with a bar graph. So taking what we just did, okay, so you notice we have the same numbers, 1/36, 1/18, 1/12, 1/9, 5/36, 1/6, and so on. Value of the roll, we've got everything from, we start with, we've got your 1/36, your 1/18, your 1/12, your 1/9, etc. Then along the bottom, we have our values that you can get. So we have 2 and 3 and 4 for sums of our rolls, all the way up to 12. And then along the side, on the bars, they marked the fractions, but then on the side, they marked the decimal. So remember, let me see if I can get these both on the screen at the same time. Yeah, there we go. Okay, so we've got 1/36, but we said 1/36 was 0.028. So they've got the side marked with the decimals. 0.028 would be a little bit more than halfway to 0.05. And then 0.056 would be a little bit past 0.05. 0.83 would be a little bit past halfway to 0.10, and so on. So it shows it over here with a decimal version, and then it shows it on the bars with the fraction version, matching up with what we had. And it asks, what do you notice about the shape? And the shape in this case is it's definitely symmetric, and it definitely is unimodal, that it just has, one value that occurs the most or is the most probable. And when we get to chapter 6, we'll see that if something is shaped like a bell curve, even if it's not exactly a normal distribution, we can still treat it like it's a normal distribution. So we're going to get to the point where we really we like these distributions because there's things that we can do with it. Okay, so what do we notice? It's unimodal. It's symmetric. So if we were to, think of this as being the middle, then you could fold it over and it, land on top of each other. This is kind of like the mirror image. And the numbers repeat on the other side. It's sort of bell-shaped. So those are some of the things that we see. So now you can make probability distributions from empirical data. So we talked in chapter 4 about how data could either be, or probabilities could either be from like rolling dice and flipping coins. That would be classical. So classical, if you remember, that was coins, dice, cards, etc. But if we have data that's from a study, hold on, having a hard time talking and writing at the same time. If it's from a study or research, then that's called empirical data. And you can make probability distributions with empirical data just like you can with classical data. So in this case, we have an experiment or research study, and they sampled 25 people of their company and recorded the number of sales that they made. So we have two sales. So this company were recording how many people got 2 sales, and there were 5 people. So the number of people with that many sales. So 2 sales, there are 5 people with 2 sales. 3 sales, there were 11 people. 4 sales, there were 6 people. And 5 sales, there were 3 people. So the most common occurring was sales of 3. There were 11 people that had 3 sales. So now we could take that and make a probability distribution from it by taking these numbers, just like we did with the dice, how many, ways can you sum to this number? We can take how many number were counted in the study and put that as a fraction. So for instance, let me just kind of redo it off to the side. So the 2, 3, 4, and 5, those are the possible number of sales. We don't have to change that. But on the bottom, instead of saying there were 5 people that made 2 sales, we're going to say 5 out of the 25 people, which could then be reduced to 1/5, which could then be reduced to 0.20. So that's where these values come from. And the 25 comes from that there were 25 people. Then we have 3 sales. There were 11 people. 11 25ths can't be reduced, but it could be changed to the decimal 0.44. 6 out of 25 again can't be reduced, but it could be switched to the decimal 0.24. 3 out of 25, 3 people out of the 25. So remember, the 3 is coming from up here. So 3 out of the 25, which is 0.10 as a decimal. So you can use empirical data or classical data. It doesn't really change how you make the table or a little bit on how you interpret it, but it definitely doesn't make much difference as to how you make it. Okay, so now we're going to look at before we're done with 5.1, we're going to look at discrete probability distribution requirements. So one of the biggest things is that the sum of the probabilities of each possible value have to sum up to 1. So if we look back to our values here, we had 5 25ths plus 11 25ths plus 6 25ths plus 3 25ths. If you sum those up, 5 plus 11 is 16, plus another 6 is 22, plus another 3 is 25. So we have 25 25ths, which sums to 1, because that's everything that could happen. If it doesn't sum to 1, either you make a mistake when you did your fractions, or you're missing a possibility. If we go up to our dice, this one's a little bit long to do, but if we took 1 plus 1 36 plus 2 36 plus 3 36 and so on, it would total up to 36, or I'm sorry, 36 36. But with the original problem with just the single die, that's pretty easy to see that if I take 1/6 and add it 6 times, I'm going to get 6 6, which is 1. So the sum of all the probabilities has to total up to 1. So now the other requirement is that the probability of each possible value must be between 1 and 0. We talked in chapter 4 about how probabilities could only go between 0 and 1, because 0 means that it absolutely can't occur, can't happen, and 1 means it absolutely must occur. And there's nothing beyond that. The highest probability you could have is a 1 or a 100%. The lowest probability you could have is a 0 or a 0%. We can't go beyond that. So let's check these two probability distributions that are written out here and see, are they really probability distributions? So the top can be anything. You don't really have to worry about the top when you're looking at, is it a probability distribution? The top can actually even be things that aren't numbers, you know, like color of hair, or what type of car you drive, or something like that. But with ours, we're going to typically stick with numbers. But it doesn't really matter what the top is. But these bottom numbers, we have to check two things. Do they sum to 1? And are they all between 0 and 1? So let's see. 0.3 plus 0.2 plus 0.1 plus 0.1. That gets us 5, 6, 7. Oh, well, that only totals to 0.7. So either they've calculated the probabilities incorrect, or they don't have all the possible x's listed. So they only add up to 0.7, so this is not a probability distribution. It is not constructed correctly for some reason. On the second one, again, we really don't care about the top. We're really just looking at these bottom numbers. So let's see. 0.2 plus 0.7 plus negative 0.3 plus 0.4. Now you have to be careful, because this gets us 9 minus 3 is 0.6 plus 0.4 would be 1. But that's not the only thing we're looking at, remember. We cannot have anything in our probabilities that is negative or larger than 1. So what does it mean that 11 has a probability of negative 0.3? That's below 0, and 0 means it can't occur. So what would a negative probability mean? It like really can't occur? It's not realistic. It's not how probabilities work. So this is not, they do all add up to 1, but they're not all between 0 and 1. So this is not a probability distribution either. So both of these have flaws. Now we're going to move on to doing some actual computations with our probability distributions. So this is section 5.2. And we're still on discrete probability distributions. And now we're going to learn how to do mean, variance, standard deviation, and expectation of discrete probability distributions. Now I'm going to say this now because it kind of gets lost in things if I wait to do it later. When you're calculating the mean of a discrete probability distribution, that is the same thing as the expectation. So the expectation is also sometimes called the expected value. And when you're playing a game or rolling die or things, what you get for the average is what you expect to get. So the expected value is the average. It doesn't mean you'll always get the average, but it is what you expect to get. It would be your best guess to guess the mean. So when we're calculating mean and when we're calculating expectation or expected value, they are the exact same calculation. They are the same thing. So this says we want to find the mean, standard deviation, expected value for a discrete random variable, which we already said. All right, so we're going to start with the mean. And we've got this big long formula, but it's not nearly as scary as it looks like. It says that the mean of a discrete random variable is the expected, it does say it here too, the mean of a discrete random variable or the expected value is E of x, or mu for mean, so expected value or mean, equals the x sub 1, which is like the first x value, the first possibility. So when we're talking about, say, the die, that would be 1. And then the probability of that happening, which if we were talking about the die, that would be 1/6. Then the next value, so if we're talking about the die, that would be 2 times 1/6, and so on until we get all of them. So x sub n means up until you've done all n values. If we write that in shorthand, this is what you'll see on your formula card that you can use on the exams. We use the summation symbol, and it says x times p of x. So we take the sum, so we are adding these all up, the sum of the x's times the p of x's. It doesn't say x sub 1, x sub 2, x sub 3. It just says the x's times p of x, which means like times their corresponding probability. And this actually ends up being a weighted mean with each value weighted by how likely it is to occur by its probability. So it's kind of similar to like when we're doing GPAs. The idea of expected value comes from gambling. For example, the expected value of playing a game of chance is the amount of money on average that you will gain or lose per play. So if you were to take a game of chance, whether that's anything that you would see in a casino, any kind of card game, anything like that, but we're mostly talking about like where you could win money. If you take and calculate the expected value, then if that comes out as a positive number, that means you're expected to win overall, to be ahead after playing many times. If you get a negative number, that means that you're expected to lose money if you play the game many times. So let's look at a probability distribution example. So here we're going to go back to our sample space of flipping 3 coins or tossing a coin 3 times. It doesn't really matter if you flip 3 coins at the same time or you flip 1 coin 3 times. It's the same thing. So we've got heads, heads, heads is one of our possibilities. And then remember, we go to 2 heads with 1 tail, and we make sure that the tail is in all 3 of the different positions that it could be in. At the end, in the middle, at the beginning. And so those are all the ways to have 2 heads and a tail. Then we're going to go to where we have 2 tails and only 1 head. And the head could be at the end, in the middle, at the beginning. It's all 3 ways that could happen. And then finally we get to all 3 tails. All 3 heads to start with and all 3 tails to end with. Now if we're going to make a probability distribution for that, we're doing a probability distribution in this case that counts the number of tails that occur. Okay, so if we look, this means, so this is number of tails. So we're looking for how many times do we get 0 tails. I'm going to try to color code this a little bit. Okay, so we have 0 tails. That only happens in this instance. There's only 1 time that we can get 0 tails, and that's if you get heads, heads, heads. Remember, there's a total of 8 ways. So all of these are going to be out of 8. So we have 1 out of the 8 ways that is no tails. Now let's go to 1 tail. Well, there's this way, and this way. So there's 3 total ways to get just 1 tail. So 3 out of the 8 ways, 3/8. Then we have how many ways to get 2 tails? Well, there's tails, tails, heads, tails, heads, tails, heads, tails, tails. There's 3 ways for that to occur. So the probability of getting 2 tails, either the first and the second, the first and the third, or the second and the third, is 3 out of the 8 ways. And then lastly, I'll use the highlighter for this one. How many ways to get all 3 tails? There's only 1 way for that to happen. And so 1 out of the 8 ways is all 3 tails. Okay, so that builds our probability distribution. Let me clean this up a little bit. It's okay, we'll just leave it. All right, so in order to find the expected value or the mean, we're going to find the expected number of tails in this situation. Now, if we use the formula, that means we're going to take 0 times 1/8. Remember, we take the x times the probability of it occurring. Go back to the formula here. So take the x times the probability of it occurring, and then just keep adding up until you've got all of them. So next we're going to do 1 times 3/8. Then we're going to do 2 times 3/8. So you can see when you've got the distribution table made, it's a pretty quick process. It's just the top number times the bottom number and add them up. And then finally we have 3 times 1/8. And if we multiply that out, we get 12/8 or 3/2, which then reduces to, or changes to a decimal of 1.5. And any of these is really appropriate. If you put any of these on an exam, I would count it as correct. Alex is probably going to require that you do 3/2 or 1.5 most of the time. It's going to require the reduced fraction or the decimal. Now, you notice that the mean is not necessarily a value that x can have. There is no way to get 1.5 tails on 3 rolls. But what we're saying, and this one is kind of interesting to look at because it's symmetric, you'll notice that you have a 1/8 chance of getting this, a 3/8 chance of getting a 1, 3/8 chance of 2, 1/8 chance of 3. It's all balanced out, and you notice it falls right between the 1 and the 2. So you have an equally likely chance of getting below 1.5 as you do it getting above 1.5. Thus, your mean ends up being 1.5. It's right in the middle. But you can't actually roll, or can't actually flip 1.5 tails. But if you did a whole bunch of flips, if you flipped the 3 coins 100 times, let's say, and you wrote down how many tails you got each time, and then you averaged all those numbers out, add them all up and divide by 100, then we would expect your average to come out to be about 1.5. And the more times you did the experiment, if you did it 1,000 times, if you did it 10,000 times, then you should get closer and closer to this expected value of 1.5 for an average. Okay, so now how do we figure out the variance and then the standard deviation of a discrete probability distribution? We're going to start with something that's very similar to what we already did. We're going to, in order to get the variance, we're going to take the sum of all the x squares times the p of x's. So not the x's, but the x squares. We're going to sum those up, just like we did before. So the top number squared times the bottom number plus the top number squared times the bottom number. And then when we get done, and you have to be really careful about this because sometimes people get so lost doing, like get involved in doing this, that they forget the last part. When you're done with that, you're supposed to subtract the mean squared. A lot of times when they give you these problems, they'll have you do the mean and then the standard variance and standard deviation because you need the mean to do the variance and standard deviation. But either way, if it's not given to you or you haven't already calculated, you'll have to calculate it. And don't forget to do that, and don't forget to square it. I'll sometimes have students that will forget to subtract it at all, and so I have students sometimes that will subtract it, but they'll forget to square it. Now remember, this formula is on your card. So you need to watch when when you're done with it, just kind of double check. Did I square them all and multiply them times my probability? Did I subtract that mu squared? And then just like before, to get the standard deviation, you're just going to take the square root of whatever you get for the variance to get the standard deviation. So let's look at our example here. So we're still going to use this same table that we had before. That way we can use the mean, as I mentioned, that we already calculated. So we already have the mean from the prior problem as being 1.5. So now how do we do this standard deviation, or this is actually for variance, how do we do that variance calculation? So we're going to start with 0, and we're going to square it and take it times 1/8. So 0 squared times 1/8. And I know you're saying to yourself, isn't 0 squared just 0? Yes, but we'll write it down to go through the process. Okay, then we're going to do 1 squared times 3/8. Then we're going to do 2 squared times 3/8. And then we're going to do 3 squared times 3/8. And there's no reason that you need to do this by hand. You can if you want to, but you don't have to. You would just type that straight into your calculator. 0 squared times, and put 1/8 in as a fraction, plus 1 squared times, put 3/8 in as a fraction, and just continue. And then at the end, remember, don't forget we're supposed to subtract the mean, which was 1.5, squared. Well, order of operations says we have to do parentheses before we do the subtraction. So we're going to calculate this first, and this all together. If you calculate this all straight through, it ends up, in this case, coming out to be a 3. And then the power, you can either just calculate that right now, or if you want to calculate it ahead of time, 1.5 squared is 2.25, but it's perfectly fine to just type into your calculator 3 minus 1.5 squared. That would be perfectly fine too. The calculator will handle the order of operations. With that being said, you could put this all into your calculator at once if you wanted to, as long as you made sure you put parentheses around this part. So you could do parentheses 0 squared times 1/8 plus 1 squared times 3/8 plus 2 squared and so on. I like to get what's in the parentheses and then subtract the mean, but if you're afraid you'll forget it, just go ahead and put it all in your calculator at once and just type, make sure you put the parentheses in. And then that comes out to be 0.75. So in this case, the variance is 0.75, and then the standard deviation would be the square root of 0.75, which is approximately 0.866. And remember, if this doesn't come out to be a nice number, just leave it in your calculator and do square root of the answer. So if you recall, if you have something that, like say you want to take the square root of this 0.1667, it would not be a good idea to do square root of 0.167. It would be a better method to do square root of the answer. And that would be a better calculation because it's not rounding until the very end. So here we get 0.408. Let me see if we get a different answer if we do square root of... I can never find the square root on this calculator. Where the heck is it at? There it is. Of 0.167. I mean, it's going to come out a little bit different, regardless. But yes, you'll notice once we get to the fourth decimal, it's different. And so if we had done it the second way, this would have rounded to 0.409 when it really should round to 0.408. So again, use that answer button on your calculator to put the number in from the prior step. And then that way you're not rounding until the very end, and it's better, more accurate calculations. Okay, so we're then going to look at expected values. Remember, expected value is the same thing as the mean. So as mentioned before, another name for the mean is expectation or expected value. And so now we're going to look at games of chance. Remember we said if you had a positive number for an expected value, that means that you would come out ahead after playing several times of the game, expected to come out ahead. If you got a negative, you would be expected to come out losing. So let's analyze a game and see if you would be expected to come out behind or ahead. So we have a game of chance where a player pays $1 to buy a lottery ticket. So the player's already down -1 because they bought the lottery ticket. Each ticket has a number from 0 to 999, and a random number from 0 to 999 is drawn. And anyone with that number wins $700. Okay, so maybe it's played daily or weekly or something like that, but it's just a $1 ticket. So to get the expected value of play, you're going to take what you could win. In fact, I'm going to make this into a probability distribution table because that's what we've been working with. So there's only two outcomes. If you win the game, you win $699. I wrote it here as 700 minus 1. Okay, because you spent $1. So you're not really winning $700. You're really winning $699. You're getting your dollar back and then an additional $699. But that only happens if you win the game. And you only win the game 1 in 1,000 times. Because you have to pick the correct number, and there's 0 to 999 numbers, which is 1,000 numbers. And so you have a 1 in 1,000 chance. All the other times, you're going to lose $1. You're going to be at -1. And that's going to happen the other 999 out of 1,000 times. And so if I multiply that, 700 minus 1, or 699, times 1 out of 1,000, and then I add that to -1 times 999 out of 1,000. I multiply that out. That comes out to be 0.30, -0.30. So that means your expected losses are 30 cents per ticket. So if you played 100 tickets, you would expect to lose 30 cents times 100. Okay, that's your expected value. Yes, could you win? Yes. But the expected value, or the average winnings of a player, are -30 cents per ticket. And even if you play 1,000 times, that doesn't mean that you're going to win. Yes, you have a 1 in 1,000 chance, but that doesn't mean you're going to win 1 out of every 1,000 plays. And so again, if you were thinking of, I'm going to play 100 times, your expected loss is going to be $30. You're going to lose $30 on average. It's kind of hard to wrap our brains around that. But basically what this is saying is that more people, more money is lost than is won. And that's why the states do this, because it brings in money for the state. Most lotteries are run by the states. And so if you if they made this so that the average win was in the positives, that means they would put more money out than they would get in. So they have to make it so that it's not fair. A fair game of chance is one where the expected value of your winnings would be 0. Whatever you spent is what you got back. But almost any game of chance that you play has a negative expected value because the house, or in this case the state, wants to win. So whether you're at a casino or you're at a any place where you're gambling, the house wants to come out ahead, so they aren't going to have fair games. They're going to have games where the player on average comes out behind, so that the house on average comes out ahead and makes money. All right, so let's do another example of expected value with comparing investments. So we have a financial advisor, and it says there's 2 types of investments you could do. Bond X has a return of 5%. That means you're going to get back 5% of your money, but a default rate of 2%. Default meaning you lose all your money. Bond Y has a return of 3%, but a lower default rate. So a lower return, but also a lower default rate. So you might be like, well, it's hard for me to tell which is better. I don't get as much back on bond Y, but I'm less likely to default. Bond X, I get a better return, but I'm more likely to default. So how do I know which is better? Which one of these is better? It's hard to tell at first glance. So if we calculate the expected values, we can compare them. So bond X says that you're going to get 5% of your investment, so $1,000 times 5%, and that's going to happen 98% of the time. And that's because the other 2%, remember we had a 2% default rate, you're going to, hold on, got the wrong sign here, you're going to lose your $1,000. So 98% of the time, you're going to get 5% off your investment. But 2% of the time, you're going to lose your entire investment. And so if we calculate that out, that comes out to be 29. Whereas with Y, we still have our $1,000, but our return rate is 3% instead of 5%. And that happens more often. That happens 99% of the time, because a 1% default rate means 99% not default. And then we're going to lose all our money, lose our $1,000, only 1% of the time, 0.01. If we calculate that out, that comes out to be 19.7. And so, theoretically, it is better to invest in bond X because it has a better expected value of return. Now, does that mean you necessarily buy bond X? Maybe not. Maybe you say, okay, that's great. I do have a better expected value, but I'm going to go with the less risky bond, even though it has a lower return rate. But theoretically, statistically, mathematically speaking, bond X is a better investment. Okay, and then we have one section left for Chapter 5, and I'm going to stop this video here and do Section 5.3 as a separate video.